Hello, my name is Tyran McAllister, and this is my presentation of the fire safety of ply-clad structures in the construction industry. For my capstone project, I've investigated how fire-resistant timber frame walls are, if constructed in accordance with the Australian standards. This video presentation is a summary of my research, methodology, and findings. I'll give you a summary of the science and understanding behind timber structures and heat transfer. Then we can discuss my 3 different experiments and findings. Finally, I'll summarize my analysis and conclusion, which details how the findings compare with the Australian standards. To start off with, let me give you a brief summary of how timber frame walls are constructed, as well as how heat travels through objects, also known as thermal conduction. Timber frame walls are usually constructed with timber studs spaced at 450 centers, with ply cladding fixed to the battens to give the walls more strength and thermal resistance. The Australian standards specify at least 12 mm ply thickness for thermal resistance. These experiments are designed to determine if this is enough. Now let me explain the concepts of heat transfer. There are 3 types of heat transfer: conduction, convection, and radiation. Conduction is the main one we're looking at, and it is how heat travels through objects. Convection is how heat can travel through the air by utilizing the flow of warm and cooler air. Radiation is a little bit more complicated. It is how objects give off special types of light that can travel through the air and heat them up. If you've ever been sunburnt, you know what I'm talking about. Now I'll explain thermal conduction in a bit more detail. It can be summarized using the formula shown. Don't worry, the formula might look a little bit scary, but as I'll go through it with you now, step by step. Q1T is the overall heat transfer that the formula will determine, being in joules per second, also known as wattage. K is known as the coefficient of thermal conductivity, and is a property of every different type of material. A is the area being examined for heat transfer in meters squared. T2 is the temperature of the hot side of the wall, and T1 is the temperature of the cold side of the wall. D is the distance between them, in millimeters. Using this knowledge and formula, we can estimate the heat transfer for different ply thicknesses, and this is what exactly I plan to do in the theoretical experiment. I will now explain the 3 types of experiments I completed. First was a physical experiment, where I tested the heat transfer of plywood in the real world, using a heating element and thermometer. The second was a theoretical experiment using the thermal conduction formula as discussed earlier. The final experiment was simulated using thermal conduction software. I tested exactly how quickly heat travels through a wall using state-of-the-art software known as Energy 2D. For the physical experiment, I used the following materials: 9 bits of 300 by 300 by 3 mm thick sheets of plywood, 1 roll of sticky tape, 1 thermometer, 2 logs of timber, 1 stopwatch, 1 steel plate, and 1 steel grate. Then to conduct the experiment, I followed this procedure. Using the sticky tape, I created the different thicknesses of plywood, making sure to use enough tape. I then created a naked flame from the logs of timber. Using the plate and grate, I constructed the assembly as shown. I then measured the temperature change across each thickness of plywood over a period of 10 minutes. These are the results. As you can see, although the thicker plywood is better at resisting the heat, there are a few anomalies. In a few places, the thermometer gets cooler, which is likely a result of the thermometer being exposed to the wind. Therefore, the data from the experiment is flawed and unreliable. For the theoretical experiment, I calculated the rate of heat transfer for each thickness of ply in a timber stud wall. As you can see, the 18 mm ply is approximately 32% more resistant to the heat than the 12 mm ply, and the 15 mm ply is 20% more resistant. For the simulated experiment, I modeled a timber stud wall and gave the air and ply similar thermal properties to those found in the real world. I then ran the experiment and gathered the data. As you can see, it gets similar results to the theoretical results initially. It starts off with a spike, with 30% and 17% values for 18 mm ply and 15 mm ply comparison, much like the theoretical results. However, this data shows a much richer picture, showing how the difference in thermal resistance between the different types of ply drastically drops as the heat continues to spread. I will now compare this decline in heat transfer to the recommendation of the Australian standards. The Australian standards recommends 12 mil ply, and I can now see why. Although the thicker the plywood, the better the insulation, it starts experiencing a serious diminishing return throughout the lifespan of a fire. I can safely say that following the Australian standards when constructing a timber house with respect to fire safety is the most cost-effective way of ensuring your property's longevity.